Hello everyone, welcome back to the second part of our Cloud Computing and Big Data lecture for today about virtualization and data center design. So you have essentially seen in the first part of the lecture that it's a very abstract topic. We started this course more or less with a very practical idea of machine learning using Apache Spark, MS Azure, clouds. But now suddenly we see that there's lots of technical ground to actually enable this, and virtualization was just one part of it, which is admittedly the most important part. So that's definitely the first we have to talk about. Now the second part of this is how I really do a data center design from this. So virtualization is a technology that is very broadly applied today. You will find it from simple laptops up to the largest cloud installations today, from a typical machine that is, just fueling perhaps one company to a setup where there are many different clouds, so-called used in hybrid, clouds that we will explore at the end of the lecture, with having in-house data, but also AWS or public clouds used at the same time. So this is all an interesting setup. Let us review how that now goes to a much more orders of scale. And this is, of course, something which is very important because we learned that cloud computing is really, or has its benefit in scaling. And this is basically now a recap of the first part where we said there are different virtual clusters that we have seen already. And they're really, in a way, completely independent from the physical cluster. I mean, completely is a wrong word in this sense that, of course, it runs on the physical cluster, but it's not limited by it. So it can span, as we see here in the illustration, 3 different physical clusters for the physical cluster for the virtual cluster one. And all of this is fueled by these virtual machines that can now live within this virtual cluster. From this, you have, of course, directly the idea that when there's something happening to one physical cluster, other physical clusters are still there with the main power of the hardware, all the CPUs and all storages. Of course, they maybe don't deliver the same performance, but as we have seen in the live migration, then quickly a next physical cluster will be basically come into play to take over. And you see also that the idea, of course, is to enhance resource utilization. So you see that this cluster here is basically used here. Physical cluster 3 is the one that maybe has some free space. There's something unused, but the majority of the clusters always today in cloud computing data centers should be, of course, utilized. And this is one key idea why benefits are of using virtualization in clouds. You can actually enhance the resource utilization enormously with it. So this goes into different directions, of course. Now we have seen that we can span this virtual cluster across different hardware entities. And so with this also goes the application partitioning. So you want to have an application. And I think a very good idea, again, is to review Spark in this. When you see that, Spark was running in different worker nodes doing executions, then we basically have seen that adding more and more worker nodes means essentially similar things like here. So you would add more and more virtual nodes, maybe, but also spanning different physical nodes. In the ideal case, you maybe even don't notice because you would just use a virtual cluster and the virtual cluster keeps expanding or decreasing. It can shrink dynamically according to the usage of Spark. It depends on how many users are using Spark simultaneously. So maybe Spark is not needed in a very big installation anymore, so the demand can shrink, and then another application can take over. You see this on the top right in the illustration. You have different applications, A, B, C, D. One of them is Spark, another one is just Hadoop, another one might be completely something different, not even machine learning, right? But this is all running on the same physical machines, just encapsulated or abstracted away in the virtual cluster. And this gives you now a really massive ability of cloud providers to have lots of applications served at the same time on the same hardware, managed by the virtual machine managers in these virtual clusters. And with this, of course, you require a very good system area network. We'll talk about this a little bit. Also, when you think about that, there is again fault tolerance, disaster recovery, what happens if I can access my node and things like this. But this is, of course, a very interesting possibility now, and in the end enables really that you can have this elastic notion, this scalable notion, which was Amazon getting very famous with their elastic compute cloud with, to really scale with the demand and can grow and shrink dynamically. We will have many examples of this when we go to lecture 6, 7, and 8, when we review Angry Birds, which started really from a really failed app. It's very funny to think about this in the light of the fact that they're very successful today, Angry Birds, and now basically really had to grow with orders of magnitudes with their users. And of course, this is true also for normal businesses. They have, sometimes maybe peaks at the end of the year. It depends when they're taxed, or it depends on, if it's a commercial retailer, it has maybe a big peak around Christmas, a big peak around Easter. So all of this resource requests are very dynamic in practice. There's a kind of normal load that you would say is a kind of average, but suddenly there are these peaks. And the clouds can just scale with these peaks. If you have it down in your cellar, if the company has their own computing center, they cannot just simply now buy lots of CPUs, not new racks, and then sell them again after Christmas. So that's not how it works. So that's why another ingredient essentially is in clouds that with this scalability, you really hook different commercial scenarios on board, and not only the gaming industry, but also many other different ones. And we will review throughout this course, of course, what are these applications. This is, again, today a very conceptual lecture, admittedly, to really understand the concepts, how really, clouds can be so successful in operating today lots of applications. Now we have some examples here. We will also have in lecture 6 and lecture 7, lecture 8, and then also in lecture 8 and 9 and 10, we will come to every more details, and even there on different levels of cloud. So when I talked about infrastructure as a service, software as a service, or platform as a service, they all have a way of using virtualization differently for different application purposes, and we will talk about it in the subsequent lectures, and all of them have really, in a way or another, used virtualization. And this is, of course, a very interesting concept that we will see and is applied in all of these different cloud vendors today. And the usage really goes from storage areas where virtual storage is applied up to different virtual clusters where really compute servers are needed for number crunches. Or, as I said, also there are virtual topologies that you create, interesting subgroups where basically network services are also in a way virtualized for different users. You want this to not, let's say, easily have access to other servers in the cluster. Again, a security consideration also we will touch base on lecture 13 later also. So you see it's really inherent in all the systems. So the question is why? So why is, very successful companies like Google, Amazon, why they do this? And if you think about also, if you're a small startup, why I should consider using them? And it's best basically seen in this, let's say, very simple illustration on the bottom, where you see the traditional little ID cost model before clouds existed 20 years ago, 10 years ago, depending on which business you are, is that you have this fixed cost in infrastructure. You would buy a server farm, you would buy a small HPC system maybe, and operate a small center, which is very much, also a building question. So you have to put it somewhere. So there would be fixed costs. We will explore later what these costs are exactly, but the problem is it's fixed. So you have to buy the machines, and once they are there, on top, of course, comes variable costs that you can always steer. It's variable in the sense that in a way you have more and more administrators. If you see there's a load decreasing or the number of users of your application is decreasing, you essentially can reduce costs by letting maybe a couple of administrators again go. So, but still the hardware is not easy to sell, right? It's something which is a fixed cost investment over years. And of course, the problem is also it needs to be newt every now and then. So today you would say maybe even more faster, especially in the light of GPUs, because we have Pascal, we have Volta, we have now the A100s. So there are new and new machines coming, and the users want new technologies. They want the new GPUs. They don't want to spend deep learning algorithms we will reveal in lecture 6 and 7 to running all night. They want the new technologies. And this is, of course, if you do it in your own, let's say, operational HPC system as a small company or as a startup, it is really a big overhead. So what could be the solution? Of course, you get rid of this fixed costs. So you essentially say it should be just variable costs. And of course, we should here mention that it's a bit misleading that these variable costs are equal. You would always say that the cloud computing cost model costs more in variable costs, right? As we already observed in some of the lectures, if you want to have memory intensive systems for Apache Spark again, right? You, of course, don't have to buy the servers anymore, so that you save a lot of costs, but you have to rent them. Right? But the good news is that you can cancel it with a button and you say, no, I don't need the Apache Spark cluster right now. I will maybe need it in a month again. So you can have really the spending in the cloud a bit more steered, and you don't sit on old hardware. You will see if you're really cutting edge and you make a lot of money with, let's say, cutting edge deep learning algorithms, and you really benefit from having, let's say, new A100s that actually succeed to the Voltas now, then you essentially say, yeah, you just pay a little bit more in the cloud, but I don't have my old Pascals, Keplers, or Volta GPUs to sit on, right? They're just gone. They're somewhere in the cloud. I don't care. I just rent my new ones that I want, and I make much more business with it because my old algorithms run much more faster. And this is really a development which is now more or less exponentially. If you see the last years, maybe decade now with the NVIDIA improvements in GPUs, if you talk about the performance ratios, we will come to this also when we think about deep learning more and the efficiency. But this is, of course, something which is then even orthogonal to the number of users, right? So if you think about now, more and more users should need it, then you need another big system that you have to buy, and then you have a big problem that essentially you have to have more and more maintenance of this. If it's larger, you need a new building. With a new building comes lots of other problems. So essentially, you don't have the scalability very quickly up and down that you could have in the cloud. And this is a cost model, so to speak, that really has stand the test of time, was quite new, because 20 or 30 years ago, you will see large installations were mostly always done by large companies in their own computing centers, and more companies now consider using the cloud. And this offers, of course, also startups. It offers new ventures which have not startup capital in the orders of magnitudes, and lots of solutions, because otherwise you had to have lots of upfront investments, right, to have this service. And in a year, I can show that my deep learning models really work. Now, today, you can directly do modeling with machine learning in the cloud, and directly with this have some results. So it's really also an interesting no upfront cost, which enables particularly startups a very good idea of how to use directly cutting edge technology by having no, let's say, large venture capital available. Now, looking into this more deeply, if you're now on the other side of the equation, if you think I'm actually an infrastructure provider, I am a cloud provider, so what we have to do, what we have to think about, what are the costs of this, what is the breakdown of the costs. And by this, you see here, right, a figure which is just an example of the so-called virtualization management gap, where you see that you have lots of server spending, of course, real hardware, you have lots of management costs along it, which means somewhere has these people, they have to maintain it. There is cables that needs to be done, and there are network switches that need to be configured. And then we have, of course, a typical cost: energy, power, cooling expense. So there are lots of expenses, what you would see is quite naturally. The interesting thing is now, by enhancing this resource utilization again, you can really have the difference here between the physical server installed that you have on the right-hand side, what you could do when you would have no virtualization. Or if you employ virtualization, you have really much more installed servers, and with this, of course, enable much more customer spending, right? Because they will pay per application. They will pay by using different servers. And of course, with this, you have much more ways of offering a broader service portfolio, as we see in Amazon or Azure or Google these days. They have a hell of a lot of services that all in one way or another use virtualization. Now, by operating this, you have to see what the costs are. And the interesting thing is now a couple of factors. And you see that over 30% is roughly the IT equipment, which is 1/3 of the equation. But you would expect that this should be a significant fraction, right? You have still hardware, you have still real metal, as I will call it, right? That you have to buy servers, disks, network cables. The interesting thing, however, is that an equal amount of cost is just the cooling, because you have a so condensed way of having all the different servers together in a small room. Basically the heat is getting really up quickly, and usually a lot of money goes into chilling and cooling down the servers. And that's why, of course, you can imagine why, for instance, Finland, CSC is a big center there for supercomputing. They have their center not in Helsinki, they have it in Kajaani, much more north, where it's, let's say, very cold on the average. So they put it to cold areas, and that's why also Iceland is a very interesting or attractive way of, let's say, having here ambient air cooling, right, for these servers already. Much better than putting it somewhere in the desert in the US, where it's hot all the time. So on the rest of the, let's say, basically third, you have around emergency power. We will review this together. Air conditioning, which should be a little bit described because it has a very specific way of cooling down the servers. It's just not making one door open and then you basically have solved the problems. And then, of course, a smaller fraction of the costs as power distribution lights and things like that. So let us review a little bit this in particular, what it means. And I think when you look at from the other side of the equation again, from what are the costs really associated to this data center, then you would see that 60% of the cost is really just going to management and maintenance. And this is interesting. So it's not really the hardware that is a big problem today in these data centers. It's the cost of running the data centers. And you will see more and more data centers that are getting larger and larger. They are just directly basically created at big dams for water repositories to get really good, agreements with the power companies, right? To get a very good deal that there's not, let's say, much electricity loss through voltage lines and so on. So they have a very good idea of placing the data centers at the right location. It's not anymore that the people don't think about this. Hence the Finland example. Right, there will be a new big, let's say, pre-exascale system at the Lumi, as it is called, the Lumi supercomputer in Finland. And this is basically operated from Helsinki, but really installed in Kajaani. And this is just another example. Of course, this is a very much a situation where you have really to think about where to go. It has security implications. You want to have it in different countries if you're someone like Google or Facebook. And in fact, some of them even don't expose where their data centers are, or all of them, just a couple of them for security reasons. Right, so, but hence you see here that, basically we have one way of putting it, problem of the cooling. Another, of course, is that you see the price performance ratio when it comes to energy. We have seen that GPUs is helping a lot to lower down the footprint. This comes through the high throughput that the GPU just runs through and having just, let's say, moderate pace of the GPUs, if you remember from our previous lectures. So the energy footprint essentially is lower through the GPUs, but still as a large data center, still large, right? And of course you cannot do everything with GPUs. So you still have, let's say, some cutting edge CPU clock frequencies you want to put in a data center. So essentially you still have the energy part. And with this, you have the kind of typical constraints where operators of data centers really have to think about how to do this. And that's why some of the data centers consider to go more north if possible, or have, let's say, different water cooling infrastructures we will talk about, but which are requiring a full lecture to have the new cutting edge technologies like warm water cooling and things like this. So just review a little bit the power efficiency of the GPU, and this is already something which continues to grow on an unprecedented scale, really, with a GPU in the terms of flops they create. You remember flop was a floating point operations per second, so the performance essentially. But here you see also that we basically increase the flop rate by not necessarily having a lot of larger energy footprint. And this is a very interesting notion of this GPUs. It is basically through a lot of benefits that it has with something like explicit management of the on-chip memory and so forth. So it has lots of aspects where the GPU is really efficient. And of course, for a data center now, that is just very incredible. But when we think about exascale in the future, it's still, let's say, a challenge to have all this kind of energy for these large systems there. And one example is, for instance, also CERN, that they had, one data center, and it is a placement problem that Geneva, in a sense, could not give them more energy, right, before they create a new power plant, which is, of course, not really taken well by the society. So in this sense, they created another data center somewhere else. It's another constraint where data centers today already have to think about, again, the energy limitations. By getting the network better and better, you can, of course, do things like you see in Kajaani, right? That's Finland is just having in the north some basically area where they basically have it placed physically, but virtually operating it by large extent via Helsinki from all the user communities. And then if you think about that, it's of course a European center in place in different, let's say, organizations, you can actually use a system wherever you are. So moving the data centers in the future is just the way to go, essentially, for different reasons, not only ambient air cooling, also, of course, space and the potential, let's say, improvements of network that we see again and again rising as well. So here's an example of one of them that you just get in, a kind of view what really the size is. And this size is loaded because if you put just small data centers in the north, as we just described, or if you operate a small data center, you miss out on one effective part of the cloud computing paradigm. And this is by large the economics of scale, as it is called. So we have seen in one of the previous diagrams really that it's actually not going extremely up that much. So the interesting aspect of the costs that are operated, these, the costs in which these data centers are operated is interesting, because you could say the larger the data center really is, the lower is the operational cost, right? When you think per units of computing that you, of course, provide. Here's one example of 11 times a football field, just computing, right? Of course, storage network goes along with it. But these large data centers, of course, can operate on a much better scale, really. That's why it's called economics of scale, than these, let's say, lower data centers, which have, let's say, lots of things to do to basically have to have the same idea of the scale and the same possibilities of the scale. Of course, operating such a big center then, on the other hand, means you have again this failure, right? As I suggested, if you have a smaller center, of course, less problems, right? If you have a bigger center, more problems. But the people and the technologies that we basically have these days have really have found a way around it. So there's this live migration, as you know, and different software technologies that enable this. But so this is a huge kind of interconnected networks of computers. And of course, that's why also the physical placement of this is not always at one location. So when we think about the terminology, just one important remark that, of course, now thinking about your background, you maybe don't know so much. You never have been in a HPC room. You never have been in a data center room. You may don't know that, but I guess some of you in the media have seen at least something like a big server or even already racks. That means largely that, of course, the people in these data centers that we just seen put not just a couple of normal metal boxes or small servers alongside it. Typically, the servers that you see there in large data centers are organized in so-called racks. So these are kind of metal boxes where you put extremely multiple servers, extreme amount of multiple servers in these racks to be operated, basically interconnected very nicely, usually not only with Ethernet, sometimes even with InfiniBand, so high network bandwidth. You have a switch topology usually that interconnects these racks of being, very dense, very interestingly with a low footprint on the hall itself. It has a very high energy footprint, but from the physical placement, if you think about the one rack is really small. It has lots of computing capacity. The same goes for storage these days with SSDs and these kind of storage arrays, but they are all put in the rack. So that's important to notice. Of course, here and there you see some data centers still operate also on commodity components. So, but even then they would consider putting parts of that in racks to organize it better than having just, let's say, lots of pizza boxes, as we sometimes call it, just around the room and being a little bit loosely coupled with a server. That you see still actually in some of the companies I work with. But let's say a data center, of course, operates in a very different way. And with this, you have, of course, different storages. You have different cache hierarchies also where you think about. And these servers is really a big business today. And that's why we basically have to think about that. This is, of course, one idea where then the future has rather a problem with. It's not the computing, it's not putting it in racks and creating bigger and bigger football field-like data centers. The problem is getting, as we discussed in one of the previous lectures, then rather actually all the data, the big data really to the storage, to the computing entity. So here we take away two factors in that. The one is assume always errors, right? And having so many interconnected racks, because they're so dense together, they create a lot of heat. And a lot of heat, if you know a little bit about computing and CPUs, is not good for CPUs. So they will be failing, they will be even broken if you don't cool them down. So this is one takeaway message. The other one is it needs to be very well interconnected and interconnected in a way that they can sustain errors again, because the hardware switch could also fail. It's not, must not be only storage that fails or computing. It could be also the switch, the network itself. So how we prepare for that? We prepare for this by assuming failure is always normal. And if you go to a Google data center, we can't do this in this lecture. My hope is that at the end of the lecture series, here we have together, we can go to Vern. We did this 2 years ago. We go to the Vern data center in Iceland. And we will look a little bit how these installations really look. Vern is situated in the Keflavik old NATO base and is also a data center which is quite interesting to look at. And all these data centers have in common that actually they know that hardware will just fail. As we discussed, of course, in different levels, the bigger the data center, the bigger, of course, the outages, switch errors. There could be also software errors that just, Yarn, as an example for Spark, will not work for some reason. All the head nodes of a Spark cluster go down, the worker nodes are still there. So there are lots of different errors that you can expect. And from the network perspective, we will see the network can have some certain topologies and put in place to really sustain error. We have seen CPU failures or storage IO failures because one SSD is maybe broken, can be taken away with the live migration and maybe by duplicate data and let's say replicate data to different locations. And this is something which has brought up a new software technology idea where I said in one of the earlier lectures Apache Hadoop is this MapReduce incarnation. We have the idea of really thinking more of bringing jobs to the data, not bringing data to the compute entities. And we will talk about this in the next lecture, actually, when we talk about the Hadoop distributed file system. So also for the failures on disk I/O, basically very closely aligned or intertwined even with the CPU failures, there is a solution for this, which is on the software level, and of course also by keeping data in different replicas. It would be too much to talk in this lecture about it. This is more about the data center design itself, but of course it lives from the fact that errors are always present, and we need to have software on the one hand and then hardware on the other hand to be prepared for this. And if you go there in all of the different data centers we have worldwide, they're all prepared for this, and very well these days, because if you pay for a cloud service, you want to have, quality of service. That's the term for it. You want to have, something for your money. You don't want to wait and say, my Apache Spark cluster is currently down. Please wait 20 hours and then we have it reinstalled for you. Right? You pay a hell of a lot of money to have it now accessible. And that's the common modus operandi in this Google Cloud centers, in Facebook data centers, even if Facebook is not necessarily user fronting, but you will see that, some bosses in Facebook will be getting very angry if you put a like and this like will appear maybe in 20 hours. So because some data centers are down or some servers have a problem where exactly your like was. This is something where, these data centers today are really well prepared by these mechanisms I already told you, I'm going to tell you now, and actually which we also will have in lecture 5. So here's one of the ideas how you at least can, sustain some errors in terms of power. We have said, okay, network, CPU, and storage, that's one part of the equation, but what do you do if the whole power is not available? Or let's say not enough power comes into the data center. This could be having different reasons. It could be the power provider company that really has, let's say, grid issues in their power grid. Could be different problems in the data center itself, where the inlet is from the power, you name it. One way of getting around with this is something called a DRUPS, a deep diesel rotary uninterruptible power supplies, which is a misleading name. It is interruptible, so in a sense that the diesel fuel will at some point stop, right? So if you don't refuel the diesel engines, then of course also the data center will stop at some point in time. Hence, this is not really a long-term solution. And wherever you go, one good example is Decode Genetics. If you go behind Decode Genetics in Vatzmütten area, you will see they have, for instance, a couple of UPSs there, right? So to be prepared if, for instance, somehow this area of Vatzmütten should be not getting enough power. So then the generators will automatically go on and then will basically give Decode Genetics still computing power. This is on the order rather of hours, right, in these installations, or potentially, depending on the size of data centers, even days. But of course, it's really not something where you have a long-term solution. This would mean refueling the diesel generators, having, let's say, large silos of diesel, and nobody really wants to do this these days. But it is a way of saying, with switching over to this power supplies, and you will find this is of course not a data center technique. You will find everywhere that this is somewhere actually installed. That is common in different companies. It's common in hospitals where the machines are needed, which are maybe not HPC machines, but different machines. So we see that, of course, in different areas in businesses, that this kind of DRUPS is actually a lifesaver if you need some power. By having the data centers bigger and bigger, that's getting, of course, more and more unrealistic to cover everyone, right? To cover everything. And with this, of course, you have a kind of scaling problem. Otherwise, you have to put much more diesel generators. And of course, with this also, the less diesel generators you have, the less hours you can provide for essentially, or the less you can cover from your installation. Still, this is a technique that works well if you don't have power. Now, another idea of this building setup that you have seen now with this troops is also the cooling systems that you have. You have to do smart cooling. As I said, today there are even full lectures just about this warm water cooling, where the whole infrastructure really matters. You have pipes underneath in the second floor. You see this here in the illustration. Right, so this is not only maybe for liquid lines, for instance, in some other installations, not the one that is illustrated here, but could be in others, where also, you know, the bottom could be all the electronic cables, things you don't see, could be playing, as here in the example, a very important role with the perforated tiles in really enabling the cooling, because of course the cold air comes from the bottom through a so-called crack air conditioning unit, and it will, you know, getting cold air on the bottom, but as we know, the servers will heat it up very quickly, and at the, you know, top of the floor, then it will be hot again, and then will be sucked in basically again in this air condition mechanism. So this is just one example of really today lots of them, and you will find even energy blueprints where the HPC or the data center is connected to whole buildings to have the energy basically, and the basically aspects which make it warm in the data center, warming the whole buildings around it. So, and then cooling with this again up, down, and getting back to the server system. So this is a hot topic these days. We could talk several lectures about this, but this is not the aim of the course, right? So this is much more technical, much more building oriented. Here we want to keep on the data center and cloud side. And this brings us to another ingredient I just told you before, where we said now we have solved the power. We said the software part of it we will do actually in the next lecture 5 when we talk about MapReduce a little bit and HDFS, a distributed file system that assumes error as normal. So what about the network? Here we have again the idea that this of course should be all interconnected. The problems in data we had seen in the logistic regression should be of course covering and basically being distributed across all the nodes. Otherwise, I don't need the other nodes to compute something. So you need an interconnection of all these nodes. And you see here a very good example that can happen daily, that, you know, one of the switches also breaks. You see this, one of the core switches even. And what basically is in place in all of these different cloud installations is really a mechanisms like here, the FAT3 switch network design, where still, let's say, the so-called pods, which is this group of different switches that you have in front of one, let's say, node or rack entity where real computing is done, still can, you know, contact all the other nodes. So you basically have different connections to be on the safe side. And this could be, of course, on different scales. Here we see different scales in terms of having the whole storages connected basically to servers with so-called SANs or storage area networks. We have already the situation that so-called LANs connect different servers with, you know, big servers. And the same is actually true for just storage which sits on the network that you can connect to. So there are all of these paradigms which are a little bit different, basically, that come to play in a data center that you as a server, you as a user, you don't really see. It's somewhere at the servers, managing your big data with storages, but also, of course, putting it alongside compute. Just for the end of the lecture, some metrics. Right, we said different dimensions of scalability we have. We have a size scalability we already know about. So we want to scale up and down with memory, storage, how many processors installed in one node, and so forth. We talked about software scalability as well. With a live migration, I can employ more and more worker nodes if I want through an Apache Spark system, which is software. So there are different scalability metrics now that you can see, which are important for a data center to be judged on. Is it an interesting data center? We touch on the way how it is applied in the scalability also in lecture 13 when we talk about the cloud computing operating systems. But of course, it's a very important topic in the cloud and data center design to think about these metrics. What is the idea? What user communities I want to serve? It's all important to think about. Also, when it comes about the application scalability, so which users will even consider the data center, it depends on the size of the problems versus the machine size. So maybe When it's idle, I want to add, let's say, more applications, or I want to increase the problem size of one application. Could be also the case. And this needs to be possible. Again, idea might be if I do a word count in documents and use Spark for it, why not, using more idle time, if there is any in the data center, to add more documents and more servers, more Apache Spark workers. If I have the money for it, of course, right? You pay. But this is different scalability notions, and technology scalability is an important part, especially now if you think about the enormous growth of GPUs, right? You want to have new technologies, new GPUs we already talked about. Now, at the end of the lecture, I would like to point to you to some very important topic that will pop up again and again: public, private, and hybrid clouds. So this is best explained, or really thinking about public clouds is something you know from Amazon, Azure, you have already used many times. But hybrid clouds are basically something where you use the open cloud that are there, the public clouds, and use them via pay-per-use, but you have also some very secure data you rather prefer in your own home institution, but every now and then you have some other data set you want to actually work with in the cloud. So you would do this in a so-called hybrid cloud setup. You would have a private cloud that is just really an intranet style of cloud, just in one organization, which is this private cloud business. And basically then you would bridge out every now and then, maybe at that peaks, as I described, at around Eastern, around Christmas, then you just use a public cloud as it is convenient, adding the scalability. And this is also a very interesting, attractive model right now, especially if you think sometimes data is really crucial. Let's say for hospitals, sometimes the real patient data is inaccessible, but some studies are actually much more to be distributed. Federated machine learning models are there that use essentially just mathematical models of patients. So you cannot track any individual patient anymore. And this is something that you maybe consider to rather compute with other hospitals together in public clouds. This is just an example how you would use that paradigm. Different businesses have different ideas how to use it. Important just before we close for today, remember that when I talk about public, private, and hybrid clouds, it's an exam question, so I want your attention. And also I see it incredibly often done wrongly. This public, private, hybrid clouds had no direct influence in this IAAS, PAAS, and SAAS we will talk about. So this is a different way how you do cloud deployments. Of course, you would say I have a public cloud that is an infrastructure as a service or offers platform as a service, so it is interconnected, but it's a completely different way of organizing and having a view how cloud's operating. Just for a notion of this, we will review, of course, the star as a service paradigm in lecture 8, 9, and 10, but we will continue next week with thinking about failures with MapReduce and Hadoop. So that's all basically for today. I encourage you to look at this video that shows a little bit the Google data center scale, and basically we see us next week.